Hello. In today's video, we're going to be looking at basically solution energy dynamics. So, when we have a solution, it only forms when energetically favorable. So, we're going to look at several different energies and kind of combine energies to form this one energy we call Gibbs free energy. But we're going to look at two energies first that make up the Gibbs free energy equation to determine if we have solution formation. We're also going to be looking at equilibrium, as a solution can be considered a equilibrium process. So the energies we're going to be looking at today are entropy. Entropy, we call this the amount of disorder or randomness in the system. And then we're going to look at enthalpy. Remember, that's our heat energy. These two are going to combine to give us Gibbs free energy. And it'll tell us if we make a solution. And then the last thing we're going to be looking at is equilibrium, which is, hopefully everybody knows at this point, but it's a state where the rate of our forward reaction is equal to the rate of our reverse reaction. We do have a forward reaction and reverse reaction occurring at this time. And it's consistently occurring, which is why we call it a dynamic equilibrium. But what's not changing is our concentrations of things. Okay, so we're going to be looking at all of these things today in this video. So, let's start out with entropy. So our randomness or disorder. Entropy itself, natural systems are going to favor entropy. You can say that the universe is always trending towards greater entropy. Now, how this comes into solutions and mixtures is that mixtures are going to have greater disorder or randomness than pure substances. So if mixtures have greater disorder or entropy than pure substances, then forming a mixture from pure substances is going to increase disorder. And that's what we want. So a solution is favored according to the thermodynamic quantity entropy. Okay, so we want this to occur. Okay. Okay, so a note: making a solution will always increase entropy. However, we have to consider enthalpy as well when we're making a solution. That's because it is not the only energy. So entropy is not the only energy included in mixture formation. So we also consider enthalpy. Okay. Now this is just a picture of what's going on, why we get increased entropy. So with a solid, it's very obvious to see why we have greater entropy when we throw it into a solution. With a solid, there's very little randomness, right? It's a repeating arrangement. We don't have the fluid movement of a solution or of a liquid. So by throwing a solid into a liquid making a solution, we are significantly increasing the disorder. We can also consider the amount of different states, how many different things are going on. So here, all we have is some solute interactions going on in our solid. So not a lot of things are going on. Once we throw it in a liquid, we have all sorts of interactions going on. And even when we add two liquids together, when they're by themselves, they're just interacting with each other. But once we add them together, there's going to be all sorts of new interactions that are going to be different microstates, which increases our disorder. So you can kind of think about the positions, the different types of positions things can be in, as the more of those you have, the greater disorder you have. Okay, now let's look at enthalpy. So we always want to make a solution according to entropy, but enthalpy is really going to determine whether we're going to make a solution or not. So this is going to be the other energy involved. In solution making. In the solution process, I guess we can call it. And we call it the overall enthalpy of our solution is called the delta H solution. But we're also going to look at a delta H solvent, delta H solute, and delta H solvent, solute. So we're looking at lots of delta H's, lots of enthalpy changes within our solution process. Okay. So, our energies, our delta H values, are based on intermolecular or intramolecular forces. So, based on intermolecular forces and intramolecular forces. Okay, so we have to think about what we're doing when we're making a solution. We're breaking interactions, we're making new interactions. Okay, so we have two substances are considered when we're talking about a solution. So specifically pure substances. So we have our solute and solvent. Okay, so with our solvent molecules, generally when we think about solute or solvent molecules, we're generally thinking almost always about a liquid solvent. We could talk about solids as well. We know that there are solid solvents, but we're almost always going to talk about liquid solvents. So most of this discussion is going to be based upon liquid solvents. So when we have solvent molecules, we're talking about solvent intermolecular forces. Okay? And then when we have solute molecules all together, I'm going to put particles actually, because we could be talking about solid or liquid here. So we are looking at solute intermolecular forces or solute intramolecular forces. So for instance, if we have a covalent compound that's being dissolved, we're talking about intermolecular forces. If we have an ionic compound like salt, we're talking about intramolecular forces. So keep all of these things in mind. So we need to, in the solution process, so we're going to talk about the solution process, we are going to have to break intermolecular or intramolecular forces holding our solvent molecules together and our solute particles together. So when we're making a solution, first we must break all the interactions that are holding our solute molecules together, or solute particles together, and we have to break all the all the interactions that are holding our solvent particles together. So this is breaking intermolecular forces or intramolecular forces. And both of these are going to be endothermic in nature. So we have to add heat energy in here. Okay? Now, that's not the only energies that are involved, only enthalpies that are involved here. After we break these solvent interactions and solute interactions, we're going to make new solute-solvent interactions. And these will be generally intermolecular forces. Of course, if we're talking about a solid, then we're going to form new intermolecular forces, or intramolecular forces. Okay, so we're producing new solute-solvent interactions, and this is going to be an exothermic process. Right? So here we are going to release energy. So first we need to break inter and intramolecular forces, that's endothermic. Then we make new intermolecular forces, an exothermic process. So we're going to require heat energy to break intermolecular forces and intramolecular forces, and we're going to release energy when we make new intermolecular forces. Now, overall, so our overall energy, or overall enthalpy, we call this delta H of solution. Delta H of solution. And it's going to be equal to all of these energies added up together. So let's just look at this real quick. So the first thing we do, we break up solvent-solvent interactions, putting space between our solvent molecules. That delta H involved is delta H, solvent, solvent. And as I said, this will be endothermic. And then the next thing we're going to do is we're going to break apart our solute-solute interactions. So this is a delta H, solute-solute. So how much energy is required to break that apart? And again, this will be endothermic. So we're making space in between our particles to mush them together, making new solvent-solute interactions which form our solution. So that's our delta H, solute, solvent. Okay, and our delta H of solution, I'm actually going to do it up here. Our delta H of solution will be a combination of all of these energies. So our delta H solution will be equal to our delta H1 plus delta H2 plus delta H3. Remember, delta H1 is solvent-solvent, delta H2 is solute-solute, delta H3 is solute-solvent. So this would be a positive, and a negative. Overall, a delta H of solution that is negative is going to be favored, because that is overall exothermic. We have a little wiggle room because we have entropy in here as well. Entropy is favored when we have a mixture. So we can have a small positive for our delta H of solution. Retry that. So a small positive, also possible. And this is because entropy is also going to play a role in this. So we need to take all of these things into account. Okay? So let's think about our different energies when we think about our solution process. So we're going to form different types of solutions. Let's first look at how or when we will have solutions form. So when will a solute dissolve? Obviously, we would like if our delta H of solution is negative, right? However, there are times we don't have to think about our delta H. For instance, if we have a gas solute gas solvent, here we're going to not really consider enthalpy because we don't consider intermolecular forces when we think about gases. So mixing gases only increases entropy. Enthalpy is not considered. Because intermolecular forces are negligible within a gas. So again, we don't really think about those. So it's always favored. So we consider this spontaneous. Okay? So it will always occur. And remember, like we said in chapter 10, back in 1211, each gas is going to act as if it alone occupies the container, so it's going to fill it completely. So remember Dalton's law with that one. Okay, with other states of matter, we have to consider our energies of our solution. So must consider enthalpy. As a general rule, you're going to have a like dissolves like mentality for this. Okay, so if we have solvent-solvent interactions, similar to the solute-solute interactions, our solute-solvent interactions are going to be similar, and we're going to have a delta H that is going to be negative or very small positive. Okay, so if we have, so we think intermolecular forces. If we have two substances, if our solute has strong intermolecular forces, or if solvent has strong intermolecular forces, our solution will have strong intermolecular forces. So that all makes sense. If we have weak intermolecular forces in our solute, weak intermolecular forces in our solvent, our solution will have weak intermolecular forces, so everything will balance out energetically. Okay, so strong, 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 weak, weak, weak. So weak intermolecular forces in solute, weak intermolecular forces in solvent will lead to a solution with weak intermolecular forces. So these will occur. Okay? But let's think about what happens if we have solvent-solute interactions that are much weaker than either our solute-solute or solvent-solvent interactions. In this case, we're going to have a delta H of solution that is largely positive. When that occurs, we have a thing that, or we have a energy that is not favorable. In this case, solution will not form. Again, we want our delta H of solution to be negative or very, very small positive. Okay, let's look at this in terms of energies somewhere around here. Here we go. So here is an exothermic solution formation. So we've got solute-solute interactions, solvent-solvent interactions. So this is the beginning. We add in the energy. That's our delta H1. That's an endothermic process. Delta H2, also an endothermic process, so that's going to separate out our solvent molecules and our solute molecules, or particles. When we do that, we get a combination of separated solute and solvent. When they combine and our solute-solvent interactions, if that is a very negative process, we will have a delta H of solution that is negative. So this would be an exothermic solution formation. Here, we're looking at an endothermic solution formation. So again, we have solute and solvent interactions that are being broken. So our solvent-solvent, or H1, solute-solute, or H2. One of these is probably going to require a lot of energy because they are going to be stronger intermolecular forces here. So they're going to have one of these being a much larger arrow. In this case, it's going to be our solute. So when we separate them out, we then put them back together, and the energy is not great enough between our solute particles and solvent particles to overcome this large value. So this H3, this solute-solvent interaction, is not as strong as our H2, our solute particles. So there we get a delta H of solution that is positive. And based on the difference in those energies, this delta H of solution could be a significant value or not significant enough to, or not very large so that entropy can actually help us out in this. So let's look at two cases where we have two solutions we can form, one exothermic, one endothermic, that you guys may be familiar with. So over on the left here, we have a delta H of solution that is less than 0. So this is an exothermic process. In this process, we have a hot pack. So if you've ever taken a hot pack and cracked it open, and it's so with a hot pack, you can hear a little cracking occurring. That is actually just a solution forming, and that solution formation is exothermic in nature, producing heat. Okay, but cold packs also occur, and they are also based on the same idea, where you take a solute and you dissolve it in a solvent. And when that occurs, we actually have a delta H of solution that is positive, which is why it's an endothermic process. Now, because of entropy, both of these solutions are going to occur. Well, this one's going to occur with or without entropy, but this one has entropy in there with it. So the delta H of solution is not too great to overwhelm our entropy value. So we still will form a solution and have an endothermic process. So don't think just because we have an endothermic delta H of solution that we will not be able to form a solution. It just has to be small enough that our entropy can overcome it. And we can look at that using what's called Gibbs free energy. So Gibbs free energy is the energy that basically tells us if a process will occur. So, for Gibbs free energy, we've got, call it delta G, and is equal to delta H minus T delta S. If we have a delta G that is negative, we have a spontaneous process. And this will occur. Without the addition of any other energy. If we have a delta G that is positive, this is non-spontaneous. And here it will not occur. So we have to think about both our delta H and our delta S. Now, looking at this equation, hopefully we see in order to get a negative delta G, so we get a delta G that is always negative, we need a delta H that is negative and a delta S that is positive. Okay, so an increase in entropy allows us to have a delta S that is positive and a delta G that is negative. If we want a delta G that is always positive, and this is not what's going to occur in a solution because we cannot have a delta S that is negative in a solution, right? Mixing is always going to occur with a delta S that is positive. But delta G that is temperature dependent a delta H that is positive, delta S that is positive. Okay, or the other way around, a delta H that is negative, delta S that is negative. But we'll be looking at this one because we have a delta S that is positive because we have solution formation, which mixture which causes a delta G increase. Okay, so here in this case, this is always, or this is spontaneous rather. So we will spontaneously mix. If we have a delta H that is positive, we need our delta S to basically overwhelm that positive value, so our delta H cannot be too large. Okay. So just keep delta G in mind. Delta G in mind will tell us whether or not we form a solution. So small positive delta H or a negative delta H with a positive delta S will result in a solution that can be formed. Okay. Now, this is just a kind of summarization of enthalpy, entropy, and Gibbs free energy. So delta H is our measuring of heat. We look at it in units of energy. Delta S is our measure of disorder, and it's going to be energy over Kelvin, and then because it is temperature dependent. And our free energy is the reactivity, how likely something is going to occur, and it's also going to be in joules or energy. Okay, the last thing we want to look at in this video is going to be equilibrium. Now that we understand, hopefully, the energies that are involved in making a solution, let's look at what it means to be soluble. So we have what's called equilibrium solubility. So it is saying that our solubility of solution is considered an equilibrium process. So what I mean by that is if we have a solid solute plus a liquid solvent, and this isn't always how it occurs, but this is generally what we think of, we can have an equilibrium between those and the solution. So going from left to right, we call this dissolution. And from right to left, we call it crystallization. So we've got equilibrium between the two processes occurring. So equilibrium is between our dissolving process. This is when solvent particles collide with the solid solute. So it's in a crystal, right? And when that occurs, this causes solute-solvent interactions to form. And when that forms, the solute detaches from the solid and dissolves. Okay. We also have crystallization. Here we're going to have our solubilized solute particles colliding. When they collide, solute-solute interactions form. And when those form, crystallization occurs. Okay. We can look at our solution itself in terms of this idea of equilibrium. So we can look at ways in which our our dynamics of our equilibrium to determine how to characterize a solution. So we're going to characterize solutions based on equilibrium. Okay. So if we have an unsaturated solution, in this case, we have a solution where the solute concentration is lower than equilibrium solubility. So in order to reach equilibrium, we need to add in more solute. So more solute can be dissolved. Okay. If we have a saturated solution, here we have that's when we're at equilibrium. Okay, so we can't add in any more solute. So it can't dissolve anymore. It will just precipitate out. Okay, so we have our max amount of solute. We can, however, if we take some extra solute and throw it in, and then heat it up, we can get what's called a supersaturated solution. So we've changed our equilibrium point by heating it up. Heating it up, our equilibrium solubility increases. So we've dissolved more solute than allowable. So here we have a system that, if at all disturbed, will cause crystallization. Okay. Until we reach our saturated solution. Okay. One last thing I wanted to go over is water and salt versus water and oil. So thinking about the whole idea of energies, let's look at our energies with water and salt, and then our energies of water and oil, and see how it is that we form a solution between water and salt, but we don't with water and oil. Okay? So, when we have, so we start out with our energy of our salt and our water. Okay? So, first thing we want to do is we want to break our hydrogen bonds, separating our water molecules. So that's our delta H1. That's the energy required to break hydrogen bonds. So I'm going to actually okay. And then we get the energy of our solution, or the first energy point. Our next energy is going to be a little bit higher. It's delta H2. That's going to be the energy required to separate our sodium chloride. So delta H2, energy to break ionic bonds. Okay, so now we've separated our water. So we've separated our water molecules, and we've separated our ions. Okay? Then the energy that is released when we form our interaction between our water molecules and our ions. This was called ion-dipole interactions. This is a strong interaction because there are so many of them. You can form a lot more water-ion interactions than you can form ion-ion interactions. Okay, now this energy is slightly higher than this energy in the case of salt. So, in this case, we actually have a delta H of solution that is a small positive. But because we have such a small delta H solution, this could be overcome by our delta G, or sorry, our delta S. So water and salt. Okay. Let's look at this in difference to water and oil. Okay, now here we start out with our stuff, our unmixed oil and water. First thing we need to do is we need to separate out our water molecules. Okay. Requires a significant amount of energy. And then we need to break dispersion forces. Between our oil particles, which is a little bit less energy. It's still a decent amount of energy, but we're going to form something called dipole-induced dipole interactions. Not a very strong force. Actually, it's a little bit. And now we have a significant difference between here. So now we have a delta H of solution. That is a large positive. Because of this, our entropy will not overcome that delta H of solution that's largely positive, so no solution forms. Here, our interaction between our water and our oil is not strong enough to overcome all the hydrogen bonds we have to break and dispersion forces we have to break with our oil and our water, or water and oil rather. Okay, that's everything. See you guys later.